Hello friends, this is Priyanka. Today we are going to solve a problem on three-stage compression refrigeration system with water intercoolers. So first I will read what is the given problem. A vapor compression system with ammonia as the refrigerant works between the pressure limits of 2 bar and 12 bar with three-stage compression. The vapors leaving the water intercoolers at pressure 4 bar and 8 bar are in saturated state. If the load is 10 tons of refrigeration, find the power required to drive 3 compressors and the coefficient of performance of the system with that of simple saturation cycle working between same overall pressure limits. So this was the given question. So let us first understand what is the given data and which factors we have to find out. Now if we observe here, the system is given with 3 compression stage. So we can say that this is the low pressure compressor, intermediate pressure compressor and high pressure compressor, and there are 2 water intercoolers in between these 3 compressors. So here there are 2 water intercoolers. Now if we observe the given data, pressure limits 2 bar and 12 bar. That means this system is working in between 2 bar and 12 bar pressure limit. So what is the minimum pressure? 2 bar, and maximum pressure 12 bar. So we know that the minimum pressure is in the evaporator. So PE is equal to 2 bar. We have to select first line on this pressure enthalpy diagram that will be provided in the examination. Now this diagram is for the ammonia refrigerant. So we have to refer here pressure, evaporator pressure 2 bar, and then the maximum pressure is the condenser pressure. So on that pressure enthalpy diagram, select the line with 12 bar pressure line. So these 2 lines are getting selected. Now what is the next data given? That is the water intercooler pressure, that is at 4 bar and 8 bar. Now if we observe this diagram, here when the refrigerant is entering in this low pressure compressor and when it is leaving, this process is 1 to 2, and then when it enters the first water cooler, that is for the process 2 to 3. So what is the water intercooler pressure? 4 bar. So we can say that P2 is equal to P3 is equal to 4 bar. So here we have to write 4, and that is P2 is equal to P3. And then the next water intercooler is at 8 bar. So here is the process 4 to 5. So we can say that P4 is equal to P5, which is equal to 8 bar. So we have to again select these lines with 4 bar pressure line and 8 bar pressure line. Now it is given that when this refrigerant is getting cooled with this water intercooler, refrigerant is reached up to the saturated vapor state. Then the next is load on the evaporator, that is Q. So we can say that this is Q is equal to 10 tons of refrigeration. And what we have to find out? We have to find out what is the power required to drive the system. And we have to also calculate what is the coefficient of performance for this system. And we have to compare this coefficient of performance of this system with coefficient of performance when the system is working in between these 2 pressure limits. That means the minimum pressure is 2 bar and maximum pressure is 12 bar, and there is no any intermediate compression stages. That means from the 2 bar the system is getting directly compressed up to 12 bar. There is no any intermediate pressures. So we can easily calculate this compression because we have to take the compression from this 2 bar up to this 12 bar directly. So let us first draw the diagram on this pressure enthalpy chart, and we will find out what are the values of enthalpies at the different points, because from that enthalpy values we can easily calculate what is the power required, then coefficient of performance. So we will consider what is the initial stage of this refrigerant. So we know that at point 1, when the refrigerant is leaving the evaporator, it is at evaporator pressure and it is at saturated vapor state. So this is the pressure enthalpy chart. So this line is at saturated liquid line. So we have to write that this is the saturated liquid line and this line is for the saturated vapor line. So here is the point 1, that is pressure 2 bar and it is at state of saturated vapor. So I will select here the point 1. And here we can say that enthalpy H1 is there. So what is the enthalpy H1? That is 1420 kilojoule per kilogram. Now if we observe, the refrigerant is entering in this low pressure compressor. So when it is entering in this low pressure compressor, it is getting compressed. So what is happening? Its pressure is getting increased. But up to which pressure it is getting increased? So here it is given that water intercooler pressure, that is 4 bar. So here low pressure compression is taking place up to a pressure of 4 bar. And it is the isentropic compression, that means entropy remains constant. So we have to find out what is the entropy at this point 1 in this pressure enthalpy diagram. So with the help of blue line, or it is in the pressure enthalpy diagram, S is equal to that enthalpy, particular enthalpy is given, that the line will be passing through this point 1. And that particular point, that is at constant enthalpy only, we have to take the compression process. So if I will take here, this is the compression process. Now we have to select this point 1 entropy. So that S value is given, that will be passing through this point 1, and which is equal to 5.564. And within that line only we have to select the point. Now we know that where will be the point 2, that is it is at entropy 5.564 and it is up to a pressure of 4 bar. So here is the pressure line of 4 bar. So if we extend this line, here is the point of intersection and this will be the point 2. Now we can easily find out what is the enthalpy at point 2. So we have to select here. So what is the value of H2? That is here H2 will be 1515 kilojoule per kilogram. Now again if we will move the next. Now here after point 2, refrigerant is entering into this water intercooler. So here the cooling process is taking place at constant pressure. So we have to keep the pressure constant, that is 4 bar, and up to which state we have to take this cooling process. Now in the problem it is given that when the cooling process is taking place, the refrigerant reached up to saturated vapor state. So here is the saturated vapor line. So we will extend this line or cooling process up to this saturated vapor line. So here will be the next point, that means point 3. So we have to show the arrow also, and now here will be the H3. Now when we observe from point 3, again refrigerant is entering into this intermediate pressure compressor. So again the compression process is done at constant entropy. What is the entropy at point 3? That is 5.367. So we have to take this constant entropy line, that is S is equal to 5.367 up to a pressure of 8 bar, because the next water intercooler pressure is 8 bar. So up to this pressure the compression process is done. So the intersection of these two lines will give us the point 4, and here if we extend this point it will give us the H4. So H4 is equal to 1525. Now again if we move the next, then there is again cooling process. So cooling process is done up to the refrigerant is reached to saturated vapor state. So and it is at constant pressure. So pressure will remain same, that is 8 bar. So we have to draw here straight horizontal line. We have to show arrow also, and here will be the next point, that is the point 5. and here it will be H5. Then again if we move next, then there is the high pressure compression. So again this compression process is taking place at constant entropy. So S is equal to 5.1186. So we have to take here the constant entropy line at the compression at the entropy of 5.1186. So I will draw here one line with 5.1186 and here will be the high pressure, that is 12 bar, that is the condenser pressure. So this high pressure compression is taking place up to a pressure of condenser pressure. So here is the 12 bar pressure line and this is the point with entropy 5.1186. So point of intersection will give us the 0.6 and what is the H6, that is 1500. So when we extend this 0.6, that is H6. So this point will give us the H6 value. So in this way we will get all the values up to the 0.6. Now again if we move next, then there is the condenser. Now here in the condenser cooling process is taking place. Now if we observe, here is the state of refrigerant is at superheated state. Now the cooling process is taking place up to the refrigerant reaches to saturated liquid line. So here we have to take the cooling process at constant pressure. So what will be the pressure? That is 12 bar, that will remain constant for this condensation. Now I will move here this 0.6 to next point, that is 7. So here will be the 0.7 and we have to show arrow. Now the enthalpy at this 0.7, because it is at saturated liquid line, we will say that HF7. Okay. Now again there is the expansion valve. So there is the expansion process that is taking place. Now this expansion process is taking place up to a pressure of evaporator pressure. Why? Because if we observe, after the expansion valve, refrigerant is entering into this evaporator. So what is the evaporator pressure? That is 2 bar, and this expansion process, that means pressure is getting decreased and enthalpy remains constant. So we have to draw here the straight vertical line because enthalpy remains constant, and here is the 2 bar pressure line, that is the evaporator pressure. So we have to write here as a 0.8. So we can easily say that what is the enthalpy? So enthalpy at HF7, which is equal to H8, and that is equal to 328. Now what is the next? That is the evaporation process. So if we observe, the 0.8 is in between saturated liquid line and saturated vapor line. That means here the liquid vapor refrigerant mixture is there. When the evaporation is taking place, the refrigerant is reached for the saturated vapor state. So we have to show that. That means here the phase change process is taking place, and for this phase change some heat is getting absorbed from the surrounding media which is to be cooled. So here the refrigeration effect is taking place in the evaporator. So we have to show that from 0.8 to 0.1 at the constant pressure of 2 bar, this refrigeration effect is taking place, and here it depends on the load on the evaporator. So here the load on evaporator is also given, that is 10 tons of refrigeration. So we can easily calculate from all these enthalpy values with this power required to drive this system, then coefficient of performance for this system and coefficient of performance between these two pressure limits. So what are the pressure limits? That is 2 bar and 12 bar. So here it is important to note that when this compression, that is here the compression is taking place with these 3 compressors, but the direct compression when it is taking place from 2 bar to 12 bar directly, then what will be the coefficient of performance? So again what we have to do, we have to extend this 12 bar pressure line. So I am extending this, and here from this 2 bar to 12 bar we have to take the constant line. So up to this we have to extend this entropy line, that is what is the S1, that is 5.564, that is the entropy at point 1. So we have to observe this line, that is this will be the entropy line. So here I will draw here with the help of dotted line. So at somewhere here at this constant entropy line up to this 12 bar pressure line, what will be the point of intersection? I will say that here the point of intersection will be 2 dash, and when we take this 2 dash to this enthalpy line, we will get the enthalpy at point 2 dash, and by using the enthalpy at point 2 dash, that is H2 dash, we can easily calculate what is the coefficient of performance between these pressure limits, that is 2 bar to 12 bar directly. So let us move for the calculations. Now we will first calculate what is the mass of refrigerant. So we know that mass of refrigerant for this evaporation process, that means it is passing through this from the point 8 to 1. So we will take here mass M is equal to refrigeration effect divided by the change in enthalpy. So for this process 8 to 1, what is the enthalpy, that is H1 minus H8, that we can take. And what is the refrigeration effect? So for that, load on the evaporator is given, that is 210 multiplied by Q, and Q is equal to 10 TR. So we have to take these values. So this is the formula, M is equal to 210 Q divided by H1 minus H8. So Q is equal to 10, and when we put all the values, we will get mass is equal to 1.92 kilogram per minute. Now from this value of mass, then we will calculate here the what is the work done. So work done is taking place at the compressors, that is low pressure, intermediate pressure and high pressure compressor. So we have to take at the time of compression what is the enthalpy difference multiplied by this mass of the refrigerant. So we will take here mass of the refrigerant as a common, and now what is the enthalpy difference? So here is the process 1 to 2. Here is the process 1 to 2, that is compression process. So enthalpy difference is H2 minus H1. Then for the next intermediate pressure, the process is 3 to 4. So this is the compression process. So we have to take H4 minus H3. And for high pressure, here is the process 5 to 6. So here is the process 5 to 6. So again we have to take here H6 minus H5. So when we take this difference, and we have to add this difference because we have to take the work done for all the compressors. So when we put the values and multiply with this mass M, we will get the value of 416.64 kilojoule per minute. Now what was our first question? We have to calculate what is the power required to drive the system. So we know that power is equal to work done by 60. So when we take this 416 by 64 divided by 60, then power is equal to 6.94 kilowatt. So this is the answer. Now next we have to calculate what is the coefficient of performance. So for this coefficient of performance means what? Refrigeration effect by work done. So work done that we have already calculated, and refrigeration effect, that is 210 Q, that is 2100 divided by 416.64, and that is equal to 5.04. Now our next question was, what is the coefficient of performance when the direct compression is taking place in between this 2 bar and 12 bar. So here from this point 1 to 2 dash, the compression process is taking place. So what is the enthalpy at this point 2 dash? That is H2 dash is equal to 1670 kilojoule per kilogram. And now we have to find out what is the coefficient of performance. So refrigeration effect will remain same, but we have to take the enthalpy difference during this compression. So how to calculate the work done? That is the enthalpy difference during this compression multiplied by the mass m. So this H2 dash minus H1, we have to take this difference multiplied by the mass m, will give us the work done for this direct compression. So we will say this W1, so it will be equal to 480 kilojoule per minute. Now coefficient of performance is equal to refrigeration effect by this W1. So which is, when we put the values, we will get the answer, that is 4.375. Now when we compare these two coefficient of performance, then we come to know that the coefficient of performance with this intermediate compression stages is higher than the direct compression process from this 2 bar to 12 bar pressure. So it is important to note that when there is the intermediate compression stages with this water intercoolers, the coefficient of performance is getting improved.